In the school year of 2021 to 2022, the Mechanical Senior Design Team of Gram-Negative, under the advisement of Emily Winfield of Design Alaska, have pursued a method of treating and managing Legionnaires bacteria within a home or business. To bring everyone up to speed on what our project is, our main goal was to prevent an outbreak of Legionnaire's disease by destroying or deactivating Legionella bacteria within a home or small business's water system. This has been primarily done and shown in research to be most effective via chemical, ultraviolet, or heat treatment. Since we are building a system for both a small home and a business, we have decided to split this into two separate designs: a UV system for the home, as it is on the better suited for the small scale, and a heat treatment system for larger buildings. To cover any more key aspects about Legionella, it was originally discovered in 1976. It propagates primarily in stagnant water. It's most infectious when aerosolized, so things like showers, faucets, and sprinklers are your highest risk. And to hold to a standard, we have been following the European Union's example of maintaining less than 1,000 colony-forming units per liter.
For our smaller facility design, we chose to use ultraviolet technology and designed a small commercial building water supply with the piping necessary for heat recirculation. The current standard UV design treats incoming water at the point of entry using mercury-based UV lamps. Unfortunately, there are some downsides to mercury-based systems. These include the need to replace bulbs every year, and that the system cannot be turned on and off without reducing the lifespan. Newer UV LED technology provides the potential for a point-of-use design where individual appliances are treated within the system. This design maximizes the LED benefits of being able to turn off and on in milliseconds. Upfront UV costs are higher than traditional mercury-based systems, however. The only additional requirement over a basic home system would be a water circulator to ensure stagnating water doesn't develop within the system.
For a heat exchanger is modeled after a tube and shell, which was inspired by the milk pasteurization machines which currently exist. How it works is you have hot water flowing counter to cold water in a tube. Ours differed slightly in that the cold water, instead of being in a tube, is in a reservoir where it can flow counter to the hot. And the reasoning behind this was so that we can tap into the hot water at any point to achieve the desired temperature. This changed in our second iteration, where we went with a plate heat exchanger, which the goal was to get the temperature to as low as possible, and then to achieve the desired temperature, you mix the cold water from the plate heat exchanger with the hot water, and you can mix that in any ratio to get the desired temperature.
We verified all our models with both MATLAB and SOLIDWORKS to determine the steady states. Then, using SOLIDWORKS, we tested for the heat distribution and the startup heat transfer rates. By iterating the codes and designs in the models, we were able to rapidly work out the final details of our designs and prepared for a final design report. With these results and evidence, we feel confident in our project. It can certainly be used to sterilize water systems to within safe levels and significantly reduce the risk of Legionnaire's disease, if not completely eliminate all but the most marginal of chances. From all of us in Team Gram-Negative, thank you for watching our video on our 2021-2022 Senior Design Project on methods to treat contaminated Legionella water. This year has been a long, hard process with COVID and health and stress of school, so we are glad to be here and to have completed such a wonderful project with you all. Thank you.